Okay. So, what is the difference between linear regression and logistic regression? If you think that I have gone a little fast, you can just replay the videos and practice it and understand anything. And if you don't understand anything, you can drop in the question box. But once again, it's all very easy stuff. As long as you guys can go through it again and again and practice it, you will be loving the whole thing. Okay. And the whole analysis thing that comes with practice. Okay. Take your data sets and practice more and more, and you will be able to do that. Okay. So, what is linear regression? That is, it predicts a continuous variable. We were having weight and pain, so we applied linear regression. Logistic regression is used when you have a categorical dependent variable. For example, how much weight gain is leading to is how much weight gain, no, sorry, once again, how many study hours did you study and did you pass and fail? Okay, so the dependent variable is did you pass and fail, and what is the dependent variable? How many hours you studied. Okay, so we have a dependent variable that is categorical. Okay, and the output is between 0 and 1, like did you pass and fail. So you have to make sure that the output should be binaries. These are some of the conditions before applying a logistic regression. Every test has its conditions. You have to make sure that those conditions are satisfied, and then you can move on. Okay, so these whole tests, first condition is data should be parametric. Second condition for Pearson was it should be for linear regression was it should be a collinear data and both variables should be quantitative. So you have to check these conditions first and then you can apply that test. Okay. Now for the logistic regression, we have some conditions. First thing, it's asking that your dependent variable should be categorical, pass and fail, and then it should be just two variable, that is pass and fail, 0 and 1. Outcome should be like that. Other things that you are not that concerned with, it's saying that it should be a linear line, and here it can be a sigmoid curve and other stuff. Okay. So logistic regression, we have if we have a dependent independent variable also, just like the linear regression, but dependent variable should be a categorical variable that should having two groups. Okay. Code 1 for men, code 2 for women, and stuff like that. Independent variable can be continuous and categorical. It can be both. It can be number of hours studied, or it can also be any other variable. It can be both quantitative, numerical, and also it can be uh, categorical variable. But we prefer that it should be a quantitative variable. Non-linear relationship should be there, and the data is needs not to be. You don't need to be specific with this thing that is it parametric or not, and is it linear or not. This is important. Once again, a minimum of 50 observations should be used and it should be in the box of two. For example, you are the owner of a business and you want to see what factors are leading to an increase in return of a customer. Okay. So, is the customer returning or not? Yes, no. So, that's the dependent variable. Okay. It's two groups. If a specific politician wins or loses, depending on hours spent during the campaign. So, hours spent, that is quantitative, and win and loss, that is a dependent variable, and it is having two groups. Okay. Okay. Let's move on to another example. A sales director for a chain of appliances store wants to find out what circumstances encourages the customers to purchase extended varieties after a major, whether they purchase or not. That is our dependent variable, and what it is depending on: age of the customer, whether a gift is offered, and price of the appliance. Okay. So these are the factors that we want to check. Age is a quantitative variable. Whether a gift is offered, yes and no, that is categorical. Price of the appliance, that is again quantitative. So now for this purpose to see the risk and cause and effect, they have applied this logistic regression. Okay. So let us apply this model and then we will be looking at the tables and we will be explaining them that stuff also. This is all about the table that it will show. Okay, so we will be looking at them, and let me open it up. Okay, so now we have to see this is our dependent variable, back pain. Okay, it is having two variables, none and swear. Okay, so and we will see the relationship between gender, what is their weight, and then we will be seeing at the year. So these are categorical, this is a quantitative. And we will see the effect of these three variables on back pain. Okay, let me analyze. I will go into regression. I will go into binary logistics. Back pain is my dependent variable. It is having two groups, none and swear, and these are my independent variables, sex, weight, and year of MBBS. In categorical section, I don't need to explain it. Options. I will choose this one, the Hosmer lame show goodness of fit model. And classification plots, I don't need. Confidence interval, I will press OK. And display at each step, include constant in model continue. Okay, so I will be explaining this stuff with to you guys. Okay, so now we have applied the logistic regression model. This time it is having a little bit more of the table. Some people are like very confused when they run this test because these are the detailed tests. Okay, I showed you guys how easy the t-test was. Chi-square was very easy. Then ANOVA was a little bit difficult. Correlation was again easy. Regression is a little difficult. So if you are an editor in a journal and someone presents you an article and they have just applied the t-test, chi-square test, you will be like, yeah, that's good, but that's not up to the mark. So for up to the mark stuff, you have to go for ANOVA, you have to go for regression. Okay, if to make your article stand out, you have to apply these tests. Okay, so now what we have here, this is the logistic regression. It has explained the summary. It has told me that your dependent variable is this because if I have made a mistake, I know. For the block zero, there it has shown me the stuff. I can ignore it for the time being. I will be moving on to the block one when it is saying that I have run the test. It has shown me two models, omnibus test or model coefficient and Hosmer lame show test. These two tests are used to explain that are your variables good or not. Okay, are your variables right or wrong? Okay, are they correlated, and is your model, is your relationship significant in a broader capacity? Is it significant or not? Okay, so I will be using these models to explain my goodness of fit model. If my sample size was good enough, like around 200, they would have come out to be significant, but right now they are not significant. For this omnibus model to be significant, its significance should be less than 0.05, but here it is not. Okay, it's showing me that your model is not good. And Hosmer and Lemshow test should be more than 0.05. So once again, it's not significant. And it's again it's showing that the model is wrong. Okay. This R square value, we will be explaining them later on. Now, this is the contingency model. Once again, here we have to see that the observed and expected pain, they should not have major differences. But now here we can see that the differences are there. In observed, it was 0, and in the expected, it was 2. So it's again showing that your model is not good. So three tests have shown the model is not good. If this was my whole data set, I would have rejected this test here and out. Okay. But now, because I know that I have just used 350 sample size, 50 sample size, of course, cannot make good predictions. So I will be like, okay, that's not a problem. I just need to increase my sample size. So for the time being, we will not be dealing with that. But I have just told you guys that Hosmer and Lemshow test should have a value more than 0.05. And the omnibus test should be less than 0.05. And in the contingency table, the observed and expected should have there should not be major differences between the observed and the expected values. Okay. Here, this one is important. I will copy it and I will paste it here. Okay. And now another thing is the classification table. That is important. The variables in equation table, that is important. Okay. I will be copying them also and I will be pasting them here because I need them to analyze my data. Okay, let's go back here to the theoretical stuff a little bit and then we will move back to the interpretation. Goodness of fit tells whether the model that we have used, it describes the variable adequately or not. And omnibus test, it is significant. If it is significant, the model is a good fit. And for it to be significant, the value should be less than 0.05. Okay, and Hosmer and Lameshaw test is significant if the value is more than 0.05. Contingency table is significant if there are no major differences in observed and expected values. Okay, so our samples to explain or to better describe, it should satisfy one of them. Okay, and the best one is it should satisfy this Hosmer and Lameshaw test. But if it is not, if it is, if the omnibus test comes out to be significant, we can choose that. But the best one is it should satisfy the Hosmer and Lameshaw test. Okay, so now further we have, once again, let me open up the interpretation. This is the interpretation. Okay, and this we also need. Also, that previous interpretation that we used of linear regression, we will be needing that too. You can get this whole interpretation from Google also, and you can also just copy it. If you stop the recording, copy it and write it and save it with yourself in Word. I have just made these slides. Whenever I'm doing the analysis, I just open up these slides. I just copy the whole interpretation and analyze my results. Okay. So once again, the values are this R square value is the same as the one we discussed beforehand in linear regression. That is how much percentage change, the percentage variance the dependent variable is causing in the independent variable. In the classification table, we have other things. Okay, so let me open up that. These were our tables. Okay, so this is the Neil-Gerke R square value. This is important to us because it is showing that there is a 13.5% variance. The independent variable predicts the dependent variable, and it indicates there's 13.0.13 and 0.13, which means that the model explains 13.5% variance in weight in pain in joints. Okay. Other things we have to see, because we have observed different variables that are being affected. Okay, so now we will have to explain each and every specific variable separately. Okay, and this is also important. This is the classification table. It is showing me that this is the sensitivity, this is the specificity, and this is the annual percentage of the model. Okay, I can also write about this, but I can also skip it. Okay, to analyze this better, it's best that you put specific variables separately. Okay, that if I was seeing a between back pain and gender, and this is like actually an odds ratio table. Okay, so I can use it better if I am adding all the factors separately. This is the most important table that you have to use to write your data. Let me make it a little bit short. Okay, yeah. The result is that we can now see that the odds that a customer who is offered, these are the values that we will be focusing on. These ones, okay? That the odds that a customer, no, that the odds of developing pain, odds of developing pain in joints in males is in female, sorry, because we showed in our correlation beforehand, in female is 1.2 times as compared to males. We saw the correlation earlier also that the females were having more. So we will, instead of writing the gender specifically, we will say that the female is 1.2 times, because this is the exponential value. Exponential value for the gift, that is exponential value Beta coefficient that has come out to be 1.28. Okay, time greater than the corresponding odds for not developing joints and pain in joints. Okay. And the odds ratio for weight is 1.037. 1.037. That means that a person who is more weighted has 1.037. That means as compared, it's just a little bit less. And then we have the years of MBBS. That is, it's around zero point 0.9. So that means that the lower the years you are in, that is, if you are in first year, mm, you have less chances of getting the pain in your joints. And if you want to explain it further, you have to explore it. You can see separately, you can see the relationship between the year of MBBS and this correlation between the pain variables that you can see either from your correlation, or you can just add this one and then check. I will show you guys how to do that once again. Okay, so we have written the independent variables are significantly predicting the dependent variable. Okay, and now F value that we can take it from the this one. Where is our F value? That is, okay, no, we will not be adding the F value here because we have not done it separately. We can just add the degree of freedom value and the exponential B value. Okay, so we will not be adding this value. We will just say that the exponential value, and we will explain it more in terms of these, that it this time more, this time show, that show. Okay, and the R square value, we will be reporting the R square value as a whole. Okay, so one thing more that you can do is that is best you analyze them all separately. Year of MBBS was a little bit confusing, that we want to see the relationship between that. So just add that for now. Correlate. No, I want to run regression analysis, binary regression, and I want to just see the relationship between year of MBBS and back pain. Okay. And I will press OK. Okay. Now it's showing me the data. It's 0.7, and yes, this is the contingency table. And then we have more, move on. Now, year of MBBS and the significance has come out to be 0.1. And here it's showing an exponential is showing a little bit different one, that is 1.5. Why it is showing different? Because now we are just seeing its effect on the pain. So okay, last time we were seeing the effects of all those three variables together, so it was comparing them in among themselves also. So that was a little different value, but now we have, when we are doing it separately, it's showing us a different value. So when you are seeing the results and the effects of all the three different variables together, you need to use that previous approach. Okay, but if you are seeing just the relationship between one and two variables, you can go for this approach, that is you analyze them separately. Okay, logistic regression is more of like an odds ratio, but a little bit a detail of odds ratio. Okay, so you report this data in the same format that you just tried. The result is that we can now see that the odds that a person is will buy this according to a logistic regression model is this and that you will see from the exponential B that will be mentioned there, and the confidence interval. And the odds ratio, we already know that if it is equal to 1, that the probability is equal. If it is more than 1, then that means the person has more chances of that event happening. And if it is less than 1, that means that the chances are less in that event of happening. Okay. So these are the different tests that you can apply on your results, and it will give a very good impression of your uh, of your article. Okay, so that's it. Thank you so much.